You have heard the story so many times, it feels like a memory. In the beginning there was nothing, and then, all at once, an explosion, and the universe came roaring out of the dark. It is a tidy picture, and almost every piece of it is wrong. The Big Bang was not an explosion in empty space. It was the stretching of space itself, with no outside to expand into and no single place where it happened. And here is the part that rarely gets said out loud. The theory we trust to describe the beginning does not actually describe the beginning at all. Run the equations back toward the first instant, and they collapse into infinity, the mathematical sound of a theory admitting it has reached its own edge. So the question, underneath every creation story ever told, is still wide open tonight. What or who actually lit the fuse, if there was a fuse to light? Settle in and hit subscribe if you're new here, because by the end of this, the beginning of everything will feel less like a settled fact and more like the most honest question we have ever asked. Now, let's slowly ease into this. Part 1. The Priest Who Imagined the Beginning. There is a question almost everyone has asked at least once, usually as a child, usually at night, and then quietly set aside because it seemed to have no answer. Where did everything come from? Not this planet, not this star, but everything, the whole of it, the entire universe. We are taught a short answer for that question now, 2 words that sound almost playful, and we repeat them with a kind of easy confidence. The Big Bang, as if the matter was settled, as if those 2 words closed the book rather than opening it. But the story behind them is far stranger than the phrase suggests, and the most honest people who have ever studied it will tell you that the question a child asks in the dark has never actually been answered. We have only learned, with extraordinary precision, exactly where our answers stop. To understand how we got here, we have to begin with one particular evening, with one particular man, in a quiet chapel in Belgium, in the year 1927. Picture the wood-panelled chapel of the Catholic University of Louvain. A priest moves through the low evening light to light a single candle, and the small flame steadies and grows. He kneels before the figure of Christ for his daily devotion, as he has done countless times, his lips moving through familiar words. When he finally rises, his eyes drift upward toward the tall windows that line the chapel walls, and beyond the glass to the first stars beginning to show themselves in the early Belgian dusk. He smiles, the way a person smiles at something they find beautiful and cannot quite stop thinking about. Because this man is not only a priest, he is also a physicist, a cosmologist, and as he looks at that starlight, he is not seeing points of decoration on a dark sky. He is seeing the end of a journey that began long before the earth existed, and he is, right now, in his mind, beginning to run that journey backward. His name is Georges Lemaitre, and he is about to imagine the beginning of the world. What makes Lemaitre such a remarkable figure to stand at the start of this story is the very tension he carried inside himself. He was a faithful Catholic priest, a man for whom a creator was not an abstraction, but the center of daily life. And yet, when it came to the making of the universe, his beliefs were curiously, deliberately quiet. He felt no need for divine intervention to explain how everything began. He did not look for a 7-day miracle written into the equations. He saw the origin of the cosmos instead as a natural consequence of natural laws and processes, something that could be proved by mathematics and read directly in the movements of the heavens themselves. Here, then, is the first surprise of our story, and we should let it sit with us for a moment. The man who gave humanity its strongest argument that the universe had a beginning was the very person with the most reason of all to read a creator into that beginning, and he refused to do it. So, let us follow his mind backward, the way he followed it that evening, because the path he traced is the path this entire video will walk. He imagines a time before any living thing, before the earth was anything more than a barren ball of rock circling a young and glowing sun. Before that, He imagines the sun itself igniting, crushed into brilliance by the patient, relentless pull of gravity acting on an enormous cloud of gas and dust. And that gas and dust, he knows, was not original. It was the wreckage of earlier stars, many generations of them, stars that had lived and died and exploded long before our own, scattering the elements they had forged out across the dark. So he pushes further back still, past those many lineages of stars, past all that chemical richness, to a time when only the lightest elements drifted through a cold and lightless cosmos, hydrogen and helium, and almost nothing else. And here is where his reasoning takes its decisive turn, the turn that changes everything. Lemaitre knew, from the mathematics he had drawn out of Einstein's theory of gravity, that space itself appeared to be expanding. If space is growing larger as time moves forward, then running time backward means space must shrink. So in the reverse chronology playing out behind his eyes, the universe contracts. Galaxies that drift apart today are driven together. That dark, gas-filled cosmos is squeezed smaller and smaller, and as it shrinks, it grows hotter, the way air heats when you compress it. The atoms are forced so tightly together that eventually even light cannot move between them, and the whole universe becomes opaque, a glowing fog with nowhere to shine. Squeeze further, and the atoms themselves break apart, first into the smaller particles that compose them, and then into something more fundamental still, until there is no ordinary matter left at all, only radiation, only energy, packed into a space smaller and hotter than anything our experience can hold. And it is here, at this point, that even Lemaitre's imagination begins to falter. The universe in his mind can become smaller still, hotter still. But what happens then? What lies at the very bottom of that contraction? At the first instant, at the moment everything began. He pushed that final, unanswerable question out of his mind, content for the evening, simply to have grasped some 13 billion years of cosmic history and folded it into the first fraction of a second. That fraction of a second, that last unreachable step, is the subject of everything that follows. It is the thing we still cannot reach. The idea Lemaitre was the first to truly champion would become known, eventually and somewhat against his wishes, as the Big Bang. And for nearly 100 years now, it has been the subject of debate, of research, of speculation, and of arguments that grew heated enough to end friendships. How did the universe begin? What was the trigger for its incredible expansion? Was there a cause at all? And if there was it a what? A blind process unfolding according to law? Or was it a who, an act of will, standing outside of everything? These are the questions that have followed the Big Bang from the moment it was born. And there is one more question underneath all of them, quieter and more unsettling. Could our minds, brains assembled from ordinary matter, brains shaped by evolution to find food and avoid danger on a single small planet, could minds like ours ever truly comprehend the answer, even if it were placed directly in front of us? There is something worth pausing on in what Lemaitre actually did that evening, because it is easy to rush past it as though it were obvious. No one had ever seen the beginning of the universe. No telescope had photographed it, no instrument had recorded it, no traveller had returned from it with a report. And yet Lemaitre claimed he could reach it, not by observing it directly, but by following a chain of mathematical reasoning drawn out of Einstein's description of gravity, link by link, into a past no eye had witnessed. He was proposing that the structure of the universe could be read backward in time, the way a detective reconstructs an event from the evidence left behind, that the present state of the cosmos quietly contains the record of its own history, if only you know how to run the equations in reverse. This is a remarkable act of confidence in the idea that the universe is not only beautiful, but legible, that its most distant past is written into its present in a language a human being can learn to read. And the strange thing is that you can perform a small version of it yourself, right now, resting here in the dark. You already know that the stars are not eternal, that they are born, that they burn, and that they die. You already know that the atoms in your own body, the iron in your blood, and the calcium in your bones were forged inside stars that exploded long before the sun existed. So you can run your own thread backward, from your body to the dead stars that made it, from those stars to the clouds of gas and dust that birthed them, from those clouds back toward a simpler and hotter and denser cosmos, until you too arrive at that final closed door. Lemaitre's gift was not merely that he could imagine this journey, it was that he could put precise numbers to every step of it, and that the numbers, drawn from a theory built for entirely different purposes, agreed with what the sky would soon reveal. For now, hold on to the image of the priest in the chapel, hold on to the candle and the starlight beyond the glass, and the man who looked at both and asked what or who set that light on its way. We will come back to him at the very end, after we have learned everything this story has to teach, and when we return to that quiet evening, the question will look entirely different. Because before Lemaitre's idea could be celebrated, it first had to survive. And it very nearly did not. To understand why a simple, almost obvious-sounding idea, that the universe had a beginning, was treated as something close to heresy, we have to go back much further than 1927. We have to go back to a time when claiming the universe had a beginning, or claiming it did not, could cost a person far more than their reputation. Part 2. The Heresy of a Beginning. It is difficult, from where we stand today, to feel how dangerous this question once was. We say the words "the universe had a beginning" and nothing happens. No one is troubled. But for most of recorded human thought, the question of whether the cosmos began or had always existed was not a matter of telescopes and measurements. It was a matter of doctrine, of philosophy, and sometimes of survival. And the reason it carried such weight is the same reason it still unsettles us in the quiet hours. A universe that simply always existed, with no beginning and no end, needs no explanation for its existence. It is just there, as it always was. But a universe that began at a particular moment demands something more. It demands an answer to the question of what came before and what set it going. The instant you accept a first moment, you have invited in the question of its cause, and that question has always felt as though it leads somewhere enormous. Before Lemaitre, the study of the cosmos had mostly concerned itself with other things, with mapping our own place within the heavens and working out what the stars were made of and how far away they sat. The grand question of whether the whole had a beginning was largely left to philosophers and theologians, and the consensus, where there was one, leaned heavily toward an eternal and unchanging order. To suggest otherwise was to step onto dangerous ground. Consider the case of a 13th century philosopher named Sigurd of Brabant. In an age when nearly every scholar in Europe worked within the framework of the Church, Sigurd took the bold and lonely position, drawn from his reading of Aristotle, that the universe was eternal, that it had no beginning at all. To us, this might sound like the cautious, almost humble option, a refusal to claim too much. But in his time, it was explosive, because an eternal universe sat awkwardly against the teaching that the world had been created. His views outraged the theologians of his day, and in the year 1277 they were formally condemned, swept up in a sweeping denunciation of propositions deemed too dangerous to teach. And the story of Sigurd's end has a dark and fitting strangeness to it. According to the legend that came down through the centuries, he was murdered by a half-mad clerk, stabbed to death with a pen, the very instrument of the ideas that had made him so many enemies. Whether the detail is true or merely the kind of story people tell about heretics, it captures something real about how charged this question was. People did not merely disagree about the beginning of the universe. They considered it worth condemning a man for, and perhaps worth killing him for. So by the time Lemaitre arrived with his expanding universe and his primeval atom, he was not stepping into an empty room. He was walking into a hall that had been echoing with this argument for centuries, and the walls still held the memory of how badly it could go. For a long time after Siger, no serious scholar wanted to touch the question of a cosmic beginning. The safe assumption, the respectable one, was that the universe in its broad strokes had always been roughly as it is now, stable and ancient and without a starting line. Lemaitre's calculations did not gently extend that picture, they overturned it. They said, in the cold and impartial language of mathematics, that there was a beginning, that it could be dated, and that the universe today still carried the momentum of that first event. And this is where we have to be honest about why the idea was so hard to swallow, because it was not only about religion, and it was not only about old condemnations. It was about that buried logical demand we have already touched. A beginning seems to require a cause. We are creatures who live entirely inside cause and effect. Everything in our experience has a reason behind it, a thing that came before and made it happen. A ball moves because something pushed it. A fire burns because something lit it. So, when we are told the universe began, every instinct we have reaches automatically for the next question. What pushed it? What lit it? And there is no comfortable place to stop. If something caused the universe, then what caused that? And if nothing caused it, if it simply began on its own out of nothing at all, that feels even harder to accept, because nothing in our daily lives has ever simply begun out of nothing. The idea of a beginning traps the mind in a corner from which there seems to be no clean exit. That trap is the true reason this story matters, and it is why the title question is split the way it is. What or who caused the Big Bang? The word what points toward a process, a mechanism, a piece of physics we might one day write down. The word who points toward an intention, an agent, a will. For most of human history, the only available answer to where everything came from was a who, because a process that could create a universe was simply unimaginable. What Lemaitre and the scientists who followed him began to do, slowly and against fierce resistance, was to ask whether the who might be replaced, or at least joined, by a what. Whether the beginning of everything might be something you could calculate, rather than something you had to take on faith. It helps to understand why the eternal universe felt so comfortable for so long, because the comfort was not stupidity, it was a kind of logic. An eternal cosmos is the only picture that does not raise the question of where everything came from. If the universe has simply always been here, with no first moment, then there is nothing to explain, no origin to account for, no awkward edge at the start of time. The question, what came before, never arises, because there is no before and no beginning for it to attach to. The mind can rest. The great philosophers who imagined an eternal order and the theologians who imagined a single creating act were both, in their different ways, reaching for an answer that would let the questioning stop somewhere. An eternal universe stops it by saying there was never a start. A creator stops it by saying the start was the work of something that needs no start of its own. What both have in common is that they close the loop. What they cannot abide is an open one. And this is exactly why a natural, calculable beginning was so disturbing. It refused to close the loop. It said, here is a first moment, here is a date you can calculate. And then it left the most pressing question of all standing wide open. If the universe began, and no creator is invoked, then what began it? Nothing in ordinary life ever simply starts on its own. A stone does not leap from the ground unbidden. A fire does not light itself in an empty room. Every beginning we have ever witnessed was caused by something that came before it, and so a universe with a beginning seems to cry out for a cause, while offering no candidate for what that cause could possibly be. Lemaitre had handed the world a beginning without a before, a start with no visible starter, And that is a profoundly uncomfortable thing to hold in the mind. It is the discomfort that drives the rest of this story. But before any of that could be tested, the idea had to get through the 20th century, and the 20th century did not roll out a welcome. Lemaitre's expanding universe was met not with applause, but with suspicion, and some of the sharpest minds of the age lined up against it. One of them would attack the idea so memorably and with such scorn that he accidentally handed it the name it carries to this day. The man's name was Fred Hoyle, and he was certain the whole notion was nonsense. Part 3. The Insult That Became a Name. Fred Hoyle was not a crank. He was one of the most brilliant and inventive astronomers of his century, a man who would later help work out how stars forge the elements inside their cores, genuine and lasting science of the first rank. So when Hoyle set himself against the idea of a cosmic beginning, he did not do it out of ignorance. He did it out of conviction, and the conviction ran right down to the foundations of how he believed a universe ought to be. Hoyle favoured a different picture entirely, one he and a few colleagues had developed, called the steady-state model. In that picture, the universe had no beginning and no end. It expanded, yes, but as it did, new matter was continuously created in the gaps, just enough to keep the overall density the same, so that the cosmos looked essentially unchanging across all of time. It was, in a sense, the modern mathematical descendant of the old eternal universe, the very idea Siger of Brabant had been condemned for centuries earlier. To Hoyle, the steady-state universe was not only elegant, it was clean. It removed the awful question of the beginning altogether. There was no first moment to explain, no trigger to identify, no uncomfortable edge where physics ran out and something else, something he distrusted, might be smuggled in. And it was exactly that smuggling he feared in the rival theory. In Hoyle's own words, the idea was that the universe started its life a finite time ago in a single huge explosion, and that the present expansion was a relic of the violence of that explosion. This, he said, seemed to him unsatisfactory even before detailed examination showed that it led to serious difficulties. He could not abide it. And in 1949, during a series of talks broadcast on the radio, he reached for a vivid, dismissive phrase to describe the theory he disliked so much. He called it this idea of a Big Bang. He meant it as a put-down. He meant to make the rival theory sound crude and faintly ridiculous, a cartoon explosion, a firework where there ought to be a serious cosmology. And in one of the great ironies in the history of science, the insult stuck. The mocking little phrase was so memorable, so easy to say, so perfectly vivid, that it escaped its origins entirely and became the permanent, almost affectionate name for the very idea Hoyle had spent his energy trying to destroy. Every time we say the words Big Bang today, we are unknowingly repeating a scornful joke made by a man who believed, to the end of his life, that the universe never began at all. Let us pause here, because there is something in Hoyle worth sitting with, something more human than a simple story of right and wrong. Hoyle's deepest objection was not really about equations. It was philosophical, almost emotional. He argued that the only reason people found the Big Bang so attractive was that the teachings of the book of Genesis, the idea of a sudden creation, a let there be light, were so thoroughly woven into the collective psyche of Western culture that a scientific theory, shaped like a creation story, felt instantly familiar and therefore true. The Big Bang, he charged, was pseudoscience, little different from an attempt to justify the existence of a creator in respectable clothing. A universe with a beginning, to Hoyle, smelled like religion wearing a lab coat. And here is the weight of it, the thing to hold on to. Hoyle was a serious scientist, and his suspicion was not stupid. The question of a beginning really does press right up against the question of a creator, exactly as he feared. He looked at a universe with a first moment and saw a door that, once opened, could not easily be closed again, a door leading straight to the who, so he tried to keep it shut. He was not defending ignorance. He was defending a particular vision of a universe that needed no explanation outside itself, and he was willing to fight the evidence to protect it. That is the quietly unsettling truth at the center of this part of the story. Even at the highest levels of human thought, what we are prepared to believe about the universe is tangled up with what we are afraid that belief might imply. Hoyle could not separate the physics from the dread of where it might lead, and so he resisted, brilliantly and stubbornly, a beginning that the heavens were about to confirm. It is worth being fair to Hoyle, because the easy version of this story turns him into a villain, and he was nothing of the kind. Fred Hoyle was one of the most creative scientific minds of the 20th century, and his greatest work bears directly on the very atoms you are made of. It was Hoyle who did more than almost anyone to work out how stars build the elements inside their cores, how the simple hydrogen and helium of the early universe is cooked, generation after generation, into the carbon and oxygen and iron that make planets and living things possible. The man who could not accept the beginning of the universe was the same man who showed us how the insides of stars assemble the periodic table. He was, by any measure, brilliant, and that is precisely what makes his resistance so instructive. His steady-state universe was not a foolish idea either. It rested on a principle he found genuinely beautiful, the notion that the universe should look essentially the same, not only from every place, but at every time, that there should be nothing special about the moment we happen to inhabit. A universe with a beginning violates that elegance, because it makes the early cosmos profoundly different from the late one, and it makes our position in time, relatively near the start of things, oddly significant. Hoyle wanted a cosmos with no privileged moments and no awkward edges, and the steady-state model gave him one, at the cost of inventing a slow, continuous creation of new matter to fill the expanding gaps. He was willing to pay that price to avoid the beginning. What this reveals is something quietly humbling about how even the finest scientific minds work. We like to imagine that scientists simply follow the evidence wherever it leads, coolly and without preference. But Hoyle shows us the truth is more human than that. He looked at the same expanding universe everyone else did, and what he was willing to conclude from it was shaped by what he hoped and feared was true. He feared that a beginning would let a creator back into physics through the side door, and so he fought the beginning with all the considerable power of his intellect. He was not defending ignorance. He was defending a vision of a self-contained, eternal cosmos, and he was prepared to argue against the evidence to protect it. The lesson is not that Hoyle was weak. It is that all of us, even the most rigorous, carry our hopes into the laboratory with us, and the universe does not care what we hope. Because while Hoyle argued, the universe was quietly preparing to settle the matter. Lemaitre's mathematics did not need to win a debate over the radio. They needed something far more powerful. They needed evidence, gathered from the real sky, by real instruments, that the universe truly was expanding. And that evidence was already being collected, far from Belgium, by a man at the eyepiece of the largest telescope in the world, who was watching the light from distant galaxies do something that no eternal, unchanging universe could ever explain. Every galaxy he looked at was running away. Part 4. The galaxies that were all running away. The man at the eyepiece was Edwin Hubble, and the telescope was the largest in the world. From the Mount Wilson Observatory, set on a ridge northeast of Los Angeles, Hubble spent his nights peering through a 100-inch aperture at some of the faintest, most distant smudges of light the human eye had ever been allowed to gather. This was patient, cold, exhausting work, hour after hour in the dark, photographing objects so dim that a single image could take an entire night to capture. And what he found there, written in that faint and ancient light, would do something no argument over the radio could ever do. It would settle the question of the beginning not with words, but with measurement. To understand what Hubble saw, we first have to understand how a star, or a whole galaxy of stars, can tell you that it is moving. Light, it turns out, carries information about motion in a way that is hidden from casual view, but unmistakable once you know how to read it. You already know the principle from sound, even if you have never named it. When an emergency vehicle races toward you with its siren wailing, the pitch sounds high, and the instant it passes and begins to speed away, the pitch drops. The siren itself has not changed. What changed is that the sound waves were bunched together as the source approached you, raising the pitch and stretched apart as it receded, lowering it. This bunching and stretching of waves from a moving source is called the Doppler effect, and it does not only happen to sound, it happens to light as well. When a source of light moves away from you, the waves of that light are stretched, just as the sound waves were. The same energy now has to cover a greater distance, so the wavelength grows slightly longer, and in the visible spectrum, longer wavelengths sit toward the red end. So light from an object that is moving away from us is shifted subtly toward red. Astronomers call this redshift, and it is one of the most useful messages the universe sends us. By measuring exactly how much the light of a distant object has been reddened, you can work out how fast that object is receding. The faster it flees, the redder its light becomes. Hubble was not the first person to notice redshift in the heavens. Others had measured it in individual objects before him. But Hubble had the great telescope, and he had the patience, and he had something even more important, a way to estimate the distances to the galaxies he was studying, so he could do what no one had done before. He could line up how far away each galaxy was against how fast it was moving and look for a pattern. And the pattern he found was about to overturn our entire picture of the cosmos, and it did so with a quiet authority that no argument could match. What he found was this: almost every galaxy he examined was redshifted. Almost every galaxy, in every direction he looked, was moving away from us. And the farther away a galaxy was, the faster it was receding. The most distant galaxies were fleeing many times faster than the nearby ones, and the relationship was orderly, a clean proportion between distance and speed. Now, at first hearing, this sounds as though it should put us right back at the center of creation. If everything is running away from us in every direction, surely we must be standing at the middle of it all, the still point from which the whole universe is fleeing. For a moment, it can feel like a return to the oldest and most flattering picture of all, the Earth at the center of the heavens. But the truth Hubble's numbers pointed to is stranger and, in a way, far more humbling. The galaxies are not flying away from us because we are special. They are flying away from each other everywhere, all at once, because the space between them is growing. Let me make that visible, because it is the single most important idea in all of cosmology, and once you truly see it, the universe never looks the same again. Imagine a loaf of raisin bread before it goes into the oven, the dough studded with raisins scattered throughout. As the dough rises and swells, every raisin drifts away from every other raisin. Pick any raisin you like and call it home. From that raisin's point of view, all the other raisins are receding, and the ones farthest away are receding fastest, simply because there is more swelling dough between them to expand. But there is nothing special about the raisin you chose. Every raisin sees exactly the same thing. There is no center raisin. The dough itself is growing, and the raisins are just along for the ride. Replace the dough with space, and the raisins with galaxies, and you have the expanding universe that Hubble had stumbled upon. We are not at the center. There is no center. Every observer in every galaxy sees all the others fleeing, and each one could be forgiven for thinking themselves the still point of it all. Let yourself stand inside that picture for a moment. You are not watching the expansion from some safe vantage outside the universe. You are inside it, embedded in it, one raisin among uncountable others. Right now, as you rest here, the space between our galaxy and the distant ones is quietly stretching, carrying those far galaxies away from us faster than any rocket could chase them. The light reaching your eyes from the most distant of them set out billions of years ago, and during the entire span of its journey, it was being stretched, reddened, drawn out by the swelling of the very space it crossed. When that ancient light finally arrives, it is not the color it began as. It is a tired, lengthened version of itself, carrying in its reddening the recorded history of how much the universe grew while the light was on its way. You are, in the simplest possible sense, surrounded by evidence of the expansion. It is falling on you constantly, soundlessly, as a gentle rain of stretched and reddened starlight, and almost no one ever stops to feel it. This was the vindication Lemaitre's mathematics had been waiting for. The expansion he had drawn out of pure theory, the expansion that implied a smaller and hotter past, the expansion that pointed back toward a beginning, was no longer a line on a chalkboard. It was measured. It was real. It was written across the entire sky in the fleeing of the galaxies. And it meant that running the clock backward was not a fantasy but a legitimate scientific exercise. If the universe is genuinely expanding, then it genuinely was smaller and hotter in the past, and the question of the first moment was no longer a matter for philosophers alone. It had become a matter for physicists. There is a subtlety here that is worth slowing down for, because it is the source of one of the most common misunderstandings about the expanding universe. When we say the galaxies are moving away, it is tempting to picture them as objects flying outward through space, like fragments thrown from a center, each one traveling across a fixed and unchanging stage. But that is not what is happening, and the difference matters enormously for everything that follows. The galaxies are not, for the most part, rushing through space. The space between them is growing. They are more like marks on the surface of a balloon, being slowly inflated than like pebbles thrown across a room. As the balloon's surface stretches, every mark drifts away from every other mark, not because the marks are moving across the rubber, but because the rubber itself is expanding beneath them. The galaxies are largely sitting still in their own neighborhoods. It is the distance between the neighborhoods that keeps increasing. This is why the most distant galaxies can recede so astonishingly fast, and why the relationship Hubble found is so clean. The farther apart two galaxies are, the more expanding space lies between them, and so the faster they separate, each additional stretch of space adding its own contribution to the total. It also means the expansion has no speed limit of the ordinary kind, because nothing is actually racing through space to break it. The space itself is free to grow as quickly as it likes. Hold this picture carefully, the swelling between things rather than the rushing of things, because it dissolves the false image of an explosion hurling debris outward, and it will matter again later when we try to understand what the beginning itself was and was not. And yet, even with the galaxies themselves seeming to take Lemaitre's side, the idea of a beginning still met resistance from the most unexpected and authoritative source imaginable. The man whose own theory of gravity had made the whole expanding universe picture possible in the first place did not want to believe it. He had seen the implication years earlier, and he had recoiled from it so strongly that he had altered his own equations to make it go away. His name was Albert Einstein, and his discomfort tells us something important about just how hard it is, even for genius, to accept that the universe might have begun. Part 5. The Man Whose Universe Refused to Sit Still. The story of the Big Bang has a strange feature that is easy to miss. The man who supplied the foundation for the entire idea spent years trying to prevent it. Models of an expanding universe were built upon Albert Einstein's general theory of relativity, the description of gravity he had completed roughly a decade before Lemaitre's paper. General relativity was, and remains, one of the greatest achievements of the human mind, a complete reimagining of gravity not as a force pulling across empty space, but as the bending and curving of space and time themselves by the presence of matter and energy. And buried inside those equations, almost from the start, was a message Einstein did not want to hear. His own theory, taken at face value, did not describe a stable, eternal universe sitting quietly in place. It described a universe that should be in motion, either expanding or contracting, but not standing still. Einstein found this deeply unwelcome. Like nearly everyone of his era, he carried the unspoken assumption that the universe, on the largest scale, was static and unchanging, an eternal stage on which the smaller dramas of stars and planets played out. A universe that had to be moving, that could not simply rest, felt wrong to him. So he did something that, in hindsight, is remarkable for what it reveals about the pull of our prior beliefs. He added a new term to his equations, by hand, a kind of counterbalancing pressure spread through all of space, tuned precisely to hold the universe still. This term, which he called the cosmological constant and introduced around 1917, had no other purpose than to keep the cosmos from moving. It was not demanded by any observation. It was inserted to protect a belief. Einstein wanted a static universe, and so he reached into the most beautiful theory he had ever built and adjusted it until it gave him one. Then Lemaitre came along, took general relativity as it actually was, and drew from it the conclusion Einstein had worked so hard to suppress. The universe is expanding. The two men met and discussed it, and Einstein's response has become one of the most famous remarks in the history of science. He told Lemaitre that his calculations were correct, but that his physics was atrocious. Sit with the strangeness of that sentence for a moment. Einstein was not saying the mathematics was wrong. He could not say that because the mathematics was sound, drawn faithfully from his own theory. What he was rejecting was the meaning of it, the physical reality it pointed toward. The numbers said the universe was expanding and therefore had a smaller past, and therefore, perhaps, a beginning. And Einstein simply could not accept that the universe would behave that way no matter what his own equations insisted. This is worth dwelling on, because it shows us that the resistance to a cosmic beginning was not only the resistance of priests and old condemnations, and not only the philosophical stubbornness of Hoyle, it reached into the mind of the single most celebrated physicist of the age. And the reason for Einstein's discomfort had shifted into new territory. For the Church, the danger of a beginning had been theological. For Einstein, the danger was different. It was the simple fact that the physics of his time had no explanation whatsoever for how such a thing could happen. There was no account of what a beginning would even look like, no mechanism, no process, nothing but a mathematical point where everything was squeezed together and the equations threw up their hands. A beginning was not merely uncomfortable. It was, in the language of physics, undescribed, a blank space where a theory ought to be. Lemaitre himself felt this limit keenly. When he extrapolated the universe all the way back, he arrived at what he called the primeval atom, a single original state that contained within it the potential for the entire, immeasurable universe to come. We can trace the beginning of time and space back to this point, he reasoned. But as for what that point actually was, what it looked like, how it behaved, even he could only gesture toward the unknown. He knew that when you compress all the matter and energy of the cosmos into an ever smaller space, the laws of physics demand that the density climb and the temperature soar. We understand reasonably well what happens to matter under extreme pressure and heat, because we can recreate slivers of those conditions in enormous particle accelerators, smashing fragments of matter together to observe, briefly, the kind of state the early universe was in. But our experiments and our understanding can only reach so far. Beyond a certain point, beyond the realm of ordinary particles and the smaller things inside them, you arrive at a compressed universe of pure energy where the familiar rules begin to fail and prediction becomes impossible. The closer you push toward that first instant, the harder it becomes to say anything at all. So the primeval atom was less an answer than a beautifully honest placeholder, a way of saying here is where our knowledge points and here is exactly where it stops. And this, in the end, is the recurring shape of our whole story. Every advance in understanding the beginning has also been an advance in mapping the precise location of our ignorance. Einstein's discomfort, far from being a failure of imagination, was in a sense correct. There genuinely was no physics for the first moment. There still is not. What he got wrong was the conclusion he drew from that absence. He took the lack of a description as a reason to deny the beginning altogether, to bend his equations and keep the universe still. The generations of physicists who came after would take the same absence as something different, not a reason to deny the beginning, but an invitation to go looking for the missing physics, to ask what, precisely, could have made a universe start. To feel the full weight of Einstein's mistake, it helps to remember just how radical his own theory had been. Before Einstein, gravity was understood as a force, an invisible pull reaching across empty space between any two masses, exactly as Isaac Newton had described it more than 2 centuries earlier. Einstein replaced that picture with something stranger and more elegant. In general relativity, gravity is not a force at all, but the shape of space and time. Matter and energy bend the fabric of space-time around them, and other objects, moving through that curved fabric, follow paths that look to us like the pull of gravity. A planet orbits a star not because a rope of force tethers them, but because the star has curved the space-time around it into a kind of valley, and the planet simply rolls along the contour. It was a complete reimagining of one of the most familiar forces in nature, and it has passed every test thrown at it for over a century, and here is the irony that should not be lost. A theory this dynamic, this alive, in which space itself bends and flexes in response to its contents, almost could not help but describe a universe in motion. A cosmos full of matter, all of it curving space-time, is not a thing that wants to sit still. It wants to collapse together under its own gravity, or it must be flying apart fast enough to resist that collapse. A static, eternal, motionless universe turns out to be the one configuration that general relativity finds unnatural, a pencil balanced impossibly on its point. Einstein had built a theory whose whole character pointed toward a changing universe, and then he had reached in and pinned it still, because a changing universe was more than he was prepared to believe. The equations were wiser than the man who wrote them. Einstein, for his part, eventually came around. As the evidence for expansion mounted, he abandoned his cosmological constant and is said to have called it the greatest blunder of his life, the one time he let a prior belief override what his own theory was telling him. The universe, it seemed, really would not sit still, no matter how badly the greatest minds wanted it to. But accepting that the universe was expanding, and accepting that it had a hot and dense past, was still not quite the same as proving it beyond all doubt. The galaxies fleeing in the sky were powerful evidence, but a determined skeptic like Hoyle could still find ways to argue. What the Big Bang needed was a fingerprint, a direct trace of that hot beginning, something left over from the fire itself. And it would arrive, as the most important discoveries so often do, completely by accident, found by 2 men who at first were convinced it was nothing more than the mess left behind by a pair of pigeons. Part 6. The Noise That Would Not Go Away. In the year 1964, in Holmdel, New Jersey, 2 researchers at Bell Laboratories were wrestling with a problem that had nothing to do with the origin of the universe. Arno Penzias and Robert Wilson were using a large and unusual instrument, a horn-shaped antenna built to catch faint radio signals, the kind of signals bounced off early communication satellites. Their work demanded extraordinary precision. To measure something so faint, you must first eliminate every other source of interference, every stray hum and hiss, until the instrument is as quiet as you can possibly make it. So they set about doing exactly that, hunting down and removing every disturbance they could find. And no matter what they did, one stubborn whisper of noise refused to go away. It was a persistent, low static, and it had 3 maddening properties. It came from every direction in the sky equally. It did not change with the time of day, and it did not change with the seasons. Whatever was producing it was not in one place, not tied to the sun, not tied to any particular star or patch of sky. It was simply everywhere, all the time, a faint and uniform hiss soaking the entire heavens. The 2 men chased it with the determination of careful experimentalists who cannot stand an unexplained signal. They checked their electronics, they checked their wiring, and they turned their suspicion, eventually, to a pair of pigeons that had taken up residence inside the great horn of the antenna, coating its interior with what the scientists dryly referred to as a white dielectric material, which is to say, droppings. Here is a thing worth picturing, because it is one of the small comedies of scientific history. 2 researchers, on the verge of one of the most important discoveries ever made about the universe, up on a ladder, cleaning bird droppings out of an antenna and shooing away pigeons, convinced that the secret to their mysterious noise was nothing grander than the mess of nesting birds. They evicted the pigeons, they scrubbed the antenna clean, and the noise remained, exactly as before, indifferent to their efforts. It was not the pigeons. It was not interference from the busy machinery of nearby New York City, some 50 kilometers away. It was not anything on Earth at all. The signal was coming from beyond our galaxy. It was, they slowly and almost unwillingly came to realize, a property of the universe itself. Let me set you there, in that moment, because it is one of the strangest brushes with the ancient past that any human being has ever had. You are standing in the cold New Jersey night beside this enormous metal horn pointed up at the dark. You have done everything right. You have removed every earthly source of noise you can imagine, climbed into the antenna, cleaned out the birds, sealed the joints, checked every connection twice. And still, in your headphones, there it is, that faint and patient hiss coming from all directions at once, the same at midnight as at noon, the same in winter as in summer. For a while, it is only an annoyance, a flaw to be fixed. And then, slowly, the truth begins to settle over you, like a chill that has nothing to do with the night air. This noise is not a flaw. This noise is older than the galaxy. This noise is the faint, cooled heat of the beginning of the universe, washing over your instruments after a journey of more than 13 billion years, and you found it while you were trying to throw it away. What Penzias and Wilson had stumbled into is now called the cosmic microwave background radiation, and it is one of the most important measurements ever made by anyone. Recall what Lemaitre's reverse chronology had predicted. If you run the universe backward, it grows smaller and denser and hotter, until the whole of it is a blazing, opaque fog of radiation. That fierce early heat did not simply vanish as the universe expanded. It was stretched along with the expanding space, its once intense waves drawn out longer and longer over billions of years, cooled and reddened far past the visible range, all the way down into faint microwaves. What began as the fire of the early universe has been smeared across the entire sky and chilled to a temperature of only about 2.7 degrees above absolute zero, the coldest temperature there can be. It is the radiation scar of the hot beginning, burned uniformly into the fabric of space, and it is everywhere, in every direction, filling all of existence with the cooled afterglow of the first fire. There is no comfortable way to explain a uniform bath of cooled heat, filling all of space in a universe that simply always existed, unchanging and eternal. Hoyle's steady-state cosmos had no good reason to be glowing faintly with the leftover warmth of a hot, dense past, because in his picture there had never been a hot, dense past. But in Lemaitre's universe, the universe that began small and fierce and has been expanding and cooling ever since, this faint glow is exactly what you would expect to find. It is precisely the fingerprint the theory had been missing. And so the accidental hiss in a New Jersey antenna did what years of argument could not. It settled the matter. The universe had a hot, dense origin. The Big Bang, the very idea Hoyle had named in mockery, was now the accepted model of the cosmos, supported by the fleeing of the galaxies, and confirmed by the relic heat washing through Penzias and Wilson's headphones. The discovery was so important that it would, in time, earn Penzias and Wilson the Nobel Prize, awarded in 1978, for a signal they had at first mistaken for the work of pigeons. And there is one more detail worth keeping, because it brings this cosmic radiation startlingly close to your own life. For those who remember the old televisions, the kind that needed an antenna and could be tuned between channels, a small fraction of the snowy static that appeared between stations, the random hissing flicker on the screen, was made of this very same cosmic microwave background, the cooled light of the beginning leaking into your living room. You have, without ever knowing it, already met the oldest light there is. It has been falling on all of us, all along. It is worth lingering on what this faint glow actually is, because once you understand it, it becomes one of the most moving things in all of science. The cosmic microwave background is not light from any star or galaxy. It is older than every star. It comes from the moment, a few 100,000 years after the beginning, when the universe had finally cooled and thinned enough for light to travel freely for the first time. Before that moment, the cosmos was an opaque fog, so hot and dense that light could not move more than a tiny distance before being scattered, the way the interior of the sun is blindingly bright, yet utterly opaque. Then, as expansion cooled everything below a critical temperature, the fog cleared all at once everywhere, and the light that had been trapped was suddenly set free to stream across the universe. That released light is what reaches us now, stretched and cooled across billions of years into faint microwaves. When we map the cosmic microwave background, we are looking at the surface of that ancient fog, the oldest light it is possible to see, a portrait of the infant universe taken when it was a tiny fraction of its present age. And the temperature of it, that 2.7 degrees above absolute zero, carries its own quiet marvel. Absolute zero is the coldest temperature there can be, the point at which all motion would cease, a limit nature never quite lets anything reach. The relic radiation of the beginning now hovers just a few degrees above that ultimate cold, a once ferocious fire banked down by 13.8 billion years of expansion into the faintest possible warmth. And it is the same temperature in every direction, to within a few parts in 100,000, as if the entire sky had been set to a single thermostat before history began. That extraordinary uniformity is not just a curiosity. It will turn out, a little later in our story, to be one of the most important clues we have about what the beginning was actually like, and about why the simplest version of it cannot be the whole truth. There is a long arc closing quietly in this discovery, and it is worth naming. Centuries earlier, a philosopher had been condemned for daring to claim the universe was eternal, the question of its beginning treated as a matter for doctrine and authority to decide. And now, in a laboratory in New Jersey, the question was being settled not by argument, not by decree, not by anyone's preference about how the universe ought to behave, but by a faint hiss in an antenna that no one could argue with. The relic heat did not care what Hoyle believed, or what the church taught, or what Einstein had wished. It was simply there, measurable, the same in every direction, exactly as a hot beginning would require, and an eternal universe could not explain. After thousands of years in which the origin of everything had been the province of philosophers and theologians, the matter was decided, in the end, by two engineers cleaning birds out of a horn and finding the warmth of creation in the static. That is a profound shift in how humanity answers its largest question, from authority to evidence, and it happened almost by accident. So by now the picture seems firmly established. The galaxies flee, the relic heat glows, the universe expanded from a hot and dense beginning some 13.8 billion years ago. The Big Bang has won. And yet, just as the celebration should begin, we run into a problem, and it is the most important misunderstanding in this entire story. Because almost everything most people picture when they hear the words Big Bang is wrong. It was not an explosion. It did not happen somewhere. And the theory we have just spent so long confirming does not actually describe the one thing everyone most wants to know about, the first instant itself. Part 7. What the Big Bang never was. Let us clear away the picture almost all of us carry, because it is wrong and because the truth hidden underneath it is far more interesting. When you hear the words Big Bang, your mind almost certainly supplies an image. A single point of light in an empty black void, a sudden, violent detonation, debris hurling outward into the surrounding darkness, the way a firework bursts against the night, or the way a bomb scatters fragments across a field. It is a natural picture, and it is encouraged by the name itself, which Hoyle chose precisely to make the theory sound like an explosion. But the Big Bang was not an explosion, and almost every part of that mental image is mistaken. Correcting it is the key that unlocks the rest of this story. The first thing to let go of is the void. An explosion happens in space. A bomb sits somewhere, in a room, in a field, and the blast travels outward through the air around it, into space that already exists. But the Big Bang was not an event that happened inside a pre-existing emptiness, because according to the theory, there was no emptiness for it to happen in. There was no surrounding void, no outside, no stage on which the show took place. The Big Bang was not an explosion in space. It was an expansion of space itself. Space was not the backdrop to the event. Space was the thing that was changing. And this is why the question that springs so naturally to mind, where did the Big Bang happen, has no answer. It did not happen at a place, because every place there is, the entire fabric of space was part of it. It happened everywhere, because everywhere was, at that moment, the whole of a much smaller universe. Return for a moment to the raisin bread, because it rescues us here too. When the dough rises, there is no single raisin where the rising begins, no center from which the swelling spreads. The dough expands everywhere at once. Now imagine shrinking that loaf backward in time, the dough contracting, all the raisins drawing closer together. There is no point at which they all rush toward one special raisin. They simply all get nearer to each other, everywhere, uniformly. Run that backward far enough, and the whole loaf becomes tiny, every raisin crowded against every other, with no center and no edge, just a small, dense, uniform whole. That is closer to the real picture. The Big Bang was not a small universe sitting inside a large empty space and then exploding outward into it. It was the entire universe, all of space, in a hot and dense state, and then expanding, everywhere at once, with no outside to expand into. Once you accept that, a second correction follows, and this one matters even more for our question. The Big Bang theory, the actual scientific model that the fleeing galaxies and the cosmic background radiation support so powerfully, is not really a theory about the first instant at all. It is a theory about what came after. Here is what physicists can genuinely do. They can take the universe as it is now and run the equations of general relativity backward, watching the cosmos grow hotter and denser. They can follow it back through the time when the first atoms formed, back through the forging of the lightest elements in the primordial furnace, back further still into a churning soup of fundamental particles, and back even into a state of almost pure radiation. And across this enormous span, the theory works astonishingly well, matching observation after observation with a precision that is one of the triumphs of modern science. This is solid ground. This is the part we genuinely understand. But as you push the clock back toward the very first moment, toward time zero, something happens to the equations. The density they predict climbs higher and higher, and the temperature soars, and as you approach that first instant, both of them race toward infinity. And an infinity, in physics, is almost never a real feature of the world. It is a warning light. When your equations start producing infinite answers, it almost always means the theory has been pushed past the limit of where it works, that it has stopped describing reality and started describing its own breakdown. The infinite density at the first instant, what physicists call a singularity, is not a confident description of a real object sitting at the start of time. It is the mathematics raising its hands and saying, I cannot go further. Beyond this point, I no longer apply. This is the single most important thing to understand about the Big Bang and the question of its cause. The theory is a magnificent description of the aftermath, of everything from a tiny fraction of a second onward. But the trigger, the first instant, the actual beginning, sits inside the gap the theory cannot cross. The Big Bang model does not tell us what caused the Big Bang. It tells us what the universe was doing immediately afterward, and then falls silent at the threshold. The beginning is not described by the theory of the beginning. It is the open wound at its center. It is worth being clear about what a singularity really is, because the word gets used as though it names a thing, when in truth it names a failure. In everyday mathematics, you meet a singularity the moment you try to divide a number by zero. The operation does not produce a strange or enormous answer. It produces no answer at all, because the question has stopped making sense. Dividing by zero is not a difficult calculation. It is a meaningless one, and when it appears in your working, it is a sign that you have asked something the mathematics cannot answer. The singularity at the beginning of the universe is the cosmic version of that. When the equations of general relativity report an infinite density at the first instant, they are not describing an infinitely dense object sitting there at the start of time. They are dividing by zero. They are telling us that we have pushed the theory into territory where it no longer functions, where its own assumptions have collapsed. This distinction changes everything about how we should think of the beginning. For a long time, people spoke of the singularity as though it were the thing itself, the true origin, an actual point of infinite density that genuinely existed at time zero. But most physicists now read it the other way around. The singularity is not a feature of the universe. It is a feature of our theory's breakdown. It marks the boundary of where general relativity can be trusted, and no further. To know what really happened at and before that boundary, we would need a deeper theory, one that joins general relativity to the rules of the very small, the quantum rules, into a single description of gravity at the smallest scales. We do not yet have that theory. And until we do, the first instant remains not an answer written in infinite numbers, but a question mark exactly where the most important answer should be. If all of this leaves you with a faint dizziness, a sense that the words are slipping out from under the ideas, that is the correct response, and it is worth honoring rather than rushing past. When we say the universe is expanding, but there is nothing outside it for it to expand into, the mind rebels, because every expansion we have ever seen, a balloon, a crowd, a stain, grows into some surrounding room. The honest reply is that the expansion of the universe is not a growth into anything. It is simply an increase in the distances between things, measured from the inside, with no exterior required and none implied. We do not infer this from philosophy, we measure it in the steady reddening of light from distant galaxies, the same redshift that started this whole story. The bigness the universe is gaining is not bigness relative to an outside. It is bigness relative to its own past, more room between the same galaxies than there used to be, and that is all the word means here. Our language was built by creatures who lived inside rooms, and it strains when we ask it to describe the thing that has no room around it. The straining is not a sign that the science is wrong. It is a sign that we have walked past the edge of the world our words were made for. And so we can begin to see the shape of an idea that will grow as we go. Perhaps the Big Bang, as we usually imagine it, is not truly the beginning of everything. Perhaps it is something more like a line drawn in the cosmic sand, a boundary that marks not the start of the universe, but the limit of our ability to describe it. The place where our finest theory runs out of road. Everything before that line is hidden from us, not necessarily because nothing was there, but because our physics cannot yet reach it. Hold on to that image, the line in the sand, because we will return to it at the very end, and when we do, it will mean something more hopeful than it sounds right now. For the moment, the honest situation is this. We know the universe was once hot and dense. We do not know what set it expanding, so the natural next question is whether physics can find a real, physical trigger to fill that gap, some process that could have put the bang into the Big Bang. And the leading candidate is an idea so strange that it makes the original theory look almost tame. It proposes that in the first unimaginable sliver of a second, space did not merely expand. It erupted, doubling and redoubling faster than light itself, in a burst so violent and so brief that it shaped everything we now see. Part 8. What put the bang in the Big Bang? To appreciate the trigger that physicists eventually proposed, we first have to understand why the simplest possible beginning does not work. For a long time, the most natural starting point seemed to be that single point of infinite density, the singularity, the place where the equations broke down. The picture was that all of time and all of space were born from one infinitely small, infinitely dense point, a one-dimensional dot containing the entire potential of the cosmos. This is not so different from the singularity thought to lurk at the center of a black hole, like the enormous one that sits at the center of our own galaxy. A black hole's singularity is a point so unimaginably dense that the pull of its gravity climbs toward infinity, so strong that not even light can escape it. A singularity at the beginning of the universe would be similar in its density, but with one difference. It would have no light to swallow and nothing outside to consume, because it already contained everything there was. It is a tidy picture, and for a while it seemed reasonable. But it carries a fatal problem, and the problem is written across the sky. If the universe truly began as an arbitrarily hot, arbitrarily dense point, then the universe that emerged from it should look a particular way. It should be lumpy. It should be wildly uneven, with enormous differences in temperature and density from one region to another, the chaotic leftovers of such a violent and concentrated origin. There should be ultra-high energy relics scattered through the cosmos, exotic remnants of that infinitely hot state. Space itself should be a mess, and it is not. When we look at the universe on the largest scales, it is astonishingly smooth and uniform. The cosmic microwave background, that relic glow of the early universe, has very nearly the same temperature in every direction we look, matching to within a tiny fraction of a degree across the entire sky. Whichever way you point your instruments, the early universe looks essentially identical, as if it had all been carefully stirred to the same temperature before it set. The fluctuations that do exist are minuscule, and they average out into a cosmos, so even that you could not tell from its large-scale texture alone which part of it you were standing in. Cosmologists describe the universe as smooth. And the chances of a single, infinitely dense point producing a universe this smooth, this evenly mixed, turn out to be vanishingly, almost impossibly small. The simplest beginning predicts a universe we do not live in. So physicists proposed something else, an idea called inflation, and it is one of the strangest proposals in all of science. The suggestion is that in the very first sliver of a moment, long before the ordinary expansion we measure today, the infant universe was filled with a peculiar kind of energy that drove space to expand, not gradually, but exponentially. Exponential growth means doubling, and then doubling again and again, each step larger than the last. Things that grow exponentially become enormous with terrifying speed. In this first instant, space doubled in size and doubled again, over and over, expanding so fast that it outran light itself. This was not light traveling through space, which has a strict speed limit. This was space itself stretching, and space is under no such restriction. In a fraction of a second, too small to picture, a region far tinier than a single atom was stretched to an enormous size. And here is why inflation is so compelling. That runaway stretching does exactly what the smooth universe demands. Take any tiny patch, small enough that it had time to even out and reach a single uniform temperature, and then blow it up to cosmic scale almost instantly. Whatever wrinkles it had are stretched flat. Whatever unevenness it carried is smoothed away. The result is a universe that is uniform and very nearly flat across enormous distances, which is precisely the smooth, flat universe the cosmic background radiation reveals to us. Inflation, in other words, is the thing that put the bang into the Big Bang. It is not the absolute beginning, but it is the violent, explosive stretching that made the universe large and smooth, the closest thing to the dramatic explosion most people imagine. According to the theory, the universe was imbued with an energy that drove this exponential expansion, and when the expansion ended, for reasons we do not fully understand, that energy was converted into matter and radiation, the ordinary stuff of the cosmos, and the slower expansion we still measure today took over. But notice what we have and have not done. We have described an explosion, a magnificent one, but we have not explained the spark that lit it. Inflation tells us the universe underwent this enormous early stretching, but it does not tell us what started the inflation, why it began, or why it ended when it did. The features of the modern universe only let us see the very last fraction of this inflationary burst, the final tiny sliver of it, a span so small, it is written as 1 divided by 10, followed by a great many zeros of a second. Everything before that final sliver, the bulk of the inflationary epoch, and whatever came before it, remains beyond our reach. We do not even know how long the inflation lasted. To feel why the smoothness of the universe is such a powerful clue, consider a puzzle that troubled cosmologists for years. Look at the cosmic microwave background in one direction, far out toward one edge of what we can see. Now look in the exact opposite direction, equally far away. The two patches of sky are at almost precisely the same temperature, matching to within a few parts in 100,000. That sounds unremarkable until you realize something. Those two patches are so far apart, and light travels at a finite speed, that in the ordinary history of the universe they could never have been in contact. Light leaving one of them at the beginning of time would not have had time to reach the other by now. They have never been able to exchange heat, never been able to share information, never been able to settle to a common temperature the way two objects do when you leave them touching, and yet they match. It is as though you met two strangers from opposite ends of the earth, who had never communicated in any way, and found they were wearing identical clothes down to the last thread. Inflation solves this puzzle in a single stroke, and that is much of why physicists take it seriously. If the entire visible universe grew from one tiny patch, small enough that its parts truly were in contact and had time to even out to a single temperature, and that patch was then stretched to enormous size faster than light in the inflationary burst, then the matching makes perfect sense. The opposite ends of the sky look identical because they were once neighbors in contact, sharing warmth, before inflation flung them unimaginably far apart. The uniformity that seemed impossible becomes the natural fingerprint of a brief era of runaway expansion. This is the kind of thing that makes a speculative idea respectable. It does not just assert that the universe inflated. It explains a specific, measured strangeness in the sky that nothing else accounts for nearly so well, even as it leaves the question of what drove the inflation entirely open. There is also a beautiful way that inflation connects back to everything we have already discussed, and it deserves a moment. When the inflationary burst ended, the energy that had been driving that runaway expansion did not simply vanish. It poured itself into ordinary matter and radiation, filling the freshly enlarged universe with a hot, dense soup of particles and light. In other words, the end of inflation is what lit the fire whose cooled relic Penzias and Wilson would stumble upon billions of years later as that faint hiss in their antenna. The cosmic microwave background, the oldest light we can see, is in a real sense the receipt for inflation's ending. The leftover heat of the moment, the great stretching stopped and handed its energy over to become the stuff of the world. So the three threads we have followed, the expanding space Hubble measured, the relic glow Penzias and Wilson found, and the inflationary burst physicists proposed, are not separate stories at all. They are one story, told from three different distances. The expansion is the present chapter, the background radiation is the photograph of an early page, and inflation is the proposed account of how the book got so large and so smooth in the first sliver of its first sentence. The pieces fit. What they still cannot tell us is how the writing began. And then comes the question that turns the whole thing back on itself. Could the inflation itself have begun with a singularity, with that infinitely small point we started with? Run the logic carefully. Exponential expansion means doubling in size as you go forward, so running it backward means halving. The universe shrinks to half its size, then a quarter, then an eighth, then a 16th, smaller and smaller without end. But here is the thing. No matter how many times you halve a number, you never actually reach zero. You can get unimaginably close, but you never arrive. From a purely mathematical point of view, a singularity of exactly zero size is an impossibility for an inflating universe. The beginning recedes from us like a horizon, always one more halving away, never quite reached. We do not have the tools to describe inflation any further back than that final sliver, and we may never have them. The origin of the inflation extends back into the fog of pre-time, beyond the reach of science, into the realm of pure speculation. So the physical trigger, the what, leads us not to an answer, but to a deeper version of the same silence. We have found a process that could have stretched the universe into the smooth, flat shape we observe. We have not found what started that process. The beginning keeps slipping just past the edge of where we can follow. And this is the moment when one of the greatest minds of the last century stepped forward to suggest something genuinely radical. Perhaps, he argued, the reason we keep failing to find what came before the beginning is not that we lack the cleverness or the instruments. Perhaps it is that the question itself, the question of a before, does not actually mean anything at all. Part 9. South of the South Pole. In the year 1981, in the shadow of St. Peter's Basilica in Vatican City, the leading cosmologists of the world gathered for a conference organized by the Pontifical Academy of Sciences. The setting carries its own quiet history. Gone were the days when the Church would issue condemnations of cosmological thinking, when a man like Sigurd of Brabant could be denounced for his views on whether the universe had a beginning. The favoured theories of this gathering, the Big Bang and its descendants, now pointed toward a mysterious origin for the universe, and the Church had made a kind of peace with the scientists mapping that origin in their own mathematical way. Among the honoured guests at this conference, in the hushed gardens and halls of the Vatican, was a 39-year-old physicist named Stephen Hawking, and he had come to present some of his latest and most unsettling thinking about the beginning of everything. Let me place you in that room, because the scene itself is unforgettable. The assembled scholars have gone quiet. At the front sits Hawking, already well into the illness that would gradually take his body from him, his physical voice failing, so that a close friend sits beside him to translate his halting words for the rest of the room to understand. There is a strange and moving contrast in the moment. His words come slowly, with difficulty, relayed through another person's mouth, and yet the thoughts behind them have never been clearer or more daring. The murmured conversations die away. Everyone leans in to catch what this man, speaking through his friend, has to say about the origin of the cosmos, and what he says will leave the room, and eventually much of the world, scrambling to understand it. The universe, Hawking proposes, is finite, but it has no edge. Someone standing at the far end of the observable cosmos, 13.8 billion light-years away, would not find a wall or a boundary or a sign saying the universe ends here. They would see space stretching around them in every direction, exactly as we do from here. There is no edge to fall off of, no border, no outside. And then he extends this idea to the dimension that matters most for our question, the dimension of time. As you trace the universe backward toward its beginning, he argues, space and time do not run into a sharp wall or a single broken point. Instead, they become fuzzy, and then they curve around and cap off, smoothly, gently, the way the surface of the Earth curves around and caps off at the South Pole. And here, he offers the analogy that would become famous, the one that captures his whole idea in a single sentence. Trying to understand what came before the universe, he says, is like asking what is south of the South Pole. The question itself is meaningless. Sit with that, because it is the strangest and most important idea in this entire story. Think about the South Pole of the Earth. It is a real place, you can stand on it, but there is no such thing as south of it. South is the direction that leads toward the pole, and once you are standing on the pole, there is no more south to go. It is not that there is a forbidden region south of the South Pole that we are not allowed to visit. It is that the words south of the South Pole do not describe any place at all. They are a grammatically correct sentence that points to nothing. Hawking's proposal is that what came before the Big Bang may be exactly like this. Before is the direction that leads toward the beginning, and once you reach the beginning, there is no more before. Not a hidden before, not a forbidden before, but no before at all. The question that has haunted this entire video, what came before, what caused it, may be a sentence that sounds meaningful and points to nothing. Let yourself feel the vertigo of that, because it is the turning point of everything we have been building toward. You have spent your whole life, as all of us have, assuming without question that there must have been a before, that something must have come first, that a beginning demands a cause, a trigger, a moment when the switch was thrown. The entire drama of this story, Lemaitre and Hoyle and Einstein, the whole century of argument, has been driven by that assumption. And Hawking does not answer the question of what came before. He does something far more disorienting. He gently removes the ground the question was standing on. He suggests that the demand for a cause rests on a hidden belief, the belief that there was a before in which a cause could sit and act. And if there was no before, if time itself curves around and caps off at the beginning the way space caps off at the pole, then there is no moment outside the universe at which a trigger could have been pulled. The cosmos would not need a cause, not because it caused itself, but because the very category of cause requires a before, and there isn't one. The universe, in this picture, does not begin in the way a race begins at a starting gun. It simply is finite and self-contained, with time tapering smoothly to a close at one end, like the lines of longitude meeting at the pole. This is what testable, rigorous science seems to be telling us, as far as it can reach. Time, in this view, is not an eternal stage that the universe was placed upon. Time is a property of the universe itself, born with it. So there was no time before the Big Bang in which anything could have happened, because there was no time at all. Space, likewise, is a property of the universe. So there was no space before the Big Bang, and there is no outside surrounding it. The cosmos is not an object sitting inside a larger emptiness. The cosmos just is. There is no exterior vantage point, no before, no beyond. And something that breaks all our intuitions this completely is nearly impossible to truly picture. We can follow the logic, we can understand the analogy of the pole, but holding the full reality of it in the mind is another matter, because our minds were built to think in terms of before and after, inside and outside, cause and effect. A reality with no before is something we can point at, but perhaps never fully feel. There is an everyday way to loosen the grip of the before question, and it helps to sit with it for a moment, because the idea is so slippery that it tends to slide out of the mind the instant you think you have grasped it. We are used to time as a kind of river that was always flowing, a stage that existed before the play began and will continue after it ends. On that picture, of course, there was a time before the Big Bang, an empty stretch of waiting, and of course something must have happened to start the show. But Hawking's proposal pulls the stage itself into the play. Time, in this view, is not the container the universe was poured into. Time is part of the universe, a feature of it, something that came into being with everything else. Ask what happened before time existed, and you are asking when something occurred in the absence of any when. The question quietly eats itself. A small analogy can help, though like all analogies it limps. Imagine asking what number comes before 1 if 1 is defined as the very first number there is. Not a negative number, not 0, but genuinely the first, with nothing prior. The honest answer is not that there is a secret number hiding before it, nor that we are forbidden to look. The answer is that the word before has simply run out of things to point at. Hawking is suggesting that the beginning of the universe may be like that, a true first, with no prior, where before stops referring to anything real. And the consequence for our whole question is enormous. If there is no before, then there is no moment in which a cause could have acted, no waiting room outside of time where a trigger could have been pulled, or a hand could have set things in motion. The universe would not be uncaused in the sense of springing from nothing through some violation of logic. It would be uncaused in the gentler sense. That cause was never an applicable idea, any more than south is applicable once you are standing on the pole. There is a quiet historical symmetry in where Hawking was standing when he said these things, and it is worth pausing on before we move forward. 7 centuries earlier, a philosopher had been condemned by the Church for arguing about whether the universe had a beginning, the question judged too dangerous to be debated freely. And here, now, in the gardens and halls of the Vatican itself, the Church had gathered the world's cosmologists to listen as one of them argued that the beginning might not even be a coherent idea. The institution that once issued condemnations was now hosting the conversation, lending its rooms to the very inquiry it had once tried to silence. That change did not happen because anyone won a shouting match. It happened because the evidence accumulated, patiently, undeniably, until the question could no longer be answered by authority and had to be handed over to measurement and mathematics. The priest who started this story would have appreciated the moment. He had always believed the two could share a world without either one ruling the other, and in that quiet Vatican assembly, with a physicist speaking through his friend about the South Pole of time, something of his hope had come true. And yet, even in the face of something this strange, the modern scientific spirit is not content to simply stop and say we cannot know. That is not how this story ends. Faced with a question that may have no answer, or may not even be a real question, scientists do something stubborn and wonderful. they keep going. They take some obscure property of the universe, or some piece of pure mathematics, and they run with it, building careful, speculative pictures of what the impossible before might be, even if Hawking is right, that there may be no before at all. And out of that refusal to stop asking have come some of the most extraordinary ideas humanity has ever produced, ideas in which our Big Bang is not the only one and not the first, but a single link in a chain of universes stretching out in both directions without end. Part 10. The universe that causes itself. There is something quietly heroic in the way science refuses to stop at the edge of the knowable. Faced with Hawking's suggestion that there may be no before, faced with equations that break down at the first instant, faced with a trigger that keeps slipping out of reach, you might expect the honest answer to be a shrug. We cannot know, so let us speak of other things. But that is not what happened. Instead, a number of physicists looked at the wall at the beginning of time and asked a different question. What if the Big Bang was not the beginning at all? What if our universe was caused by something, but that something was not a creator standing outside of time, and not a singular first moment, but simply another universe, or another phase of this one, that came before? What if the cosmos causes itself over and over, forever? The first and most intuitive version of this idea is called the Big Bounce. The picture is of an eternal universe that does not have a single birth and a single death, but instead breathes, expanding and contracting in an endless cycle. In one phase, space expands outward, driven by something like our Big Bang. Eventually that expansion slows, halts, and reverses, and the universe begins to contract, all its matter and galaxies falling back together in what would be called a big crunch. And then, instead of collapsing all the way down into the dreaded singularity, the universe bounces. The trick that makes the bounce possible lies in the strange rules of the very small. When everything is compressed to a sufficiently tiny scale, the smooth laws of ordinary physics give way to the rules of quantum mechanics, and those rules allow for a process called quantum tunneling, in which a system can jump instantaneously from one state to another without passing through the impossible middle. A contracting universe on the very edge of total collapse could tunnel straight across the forbidden point, from a contracting state to an expanding one in a single quantum leap. Our Big Bang, in this picture, was the rebound from the death of a previous universe, the upswing after a prior crunch. It is a beautiful idea, and it has one serious problem which comes directly from observation. For the Big Bounce to work, our current expansion must one day slow down and reverse, pulled back by the gravity of all the matter in the cosmos. But when we measure the expansion of the universe today, we find that it is not slowing down at all, it is speeding up. Some mysterious influence is driving the galaxies apart faster and faster, and an accelerating expansion does not look like a universe preparing to fall back together for another crunch. It looks like a universe flying apart for good. This is a genuine obstacle for the simplest cyclic models, and it has pushed physicists towards stranger and more subtle versions of the eternal universe idea. One of the most remarkable came in the year 2010 from the British physicist Roger Penrose, and it is called conformal cyclic cosmology. It is built on a piece of mathematics called conformal geometry, which concerns the shape of things irrespective of their size. Think of a chessboard. A chessboard has the same essential geometry, the same arrangement of 64 squares, the same proportions, whether it is a tiny travel set that fits in your pocket or an enormous board laid out across a garden. Shrink it or grow it, and the game is identical, because what defines a chessboard is its shape, not its scale. Penrose applies this principle to the universe as a whole, and reaches an almost dizzying conclusion. Consider the far future of our universe, Google upon Google of years from now, when every star has died, when even the black holes have evaporated away, when there is nothing left but a thin, cold, featureless bath of radiation drifting through an enormous emptiness. In that state, Penrose argues, the universe has lost all sense of scale. With no matter left to act as a ruler, there is nothing to measure size against, and a huge, cold, empty cosmos becomes geometrically equivalent, in the language of conformal geometry, to a tiny, hot, dense one. Although a giant, frozen universe and a microscopic blazing one seem about as different as two things could possibly be, in their shape, in their conformal geometry, they are the same. And so Penrose proposes that the cold, dead end of our universe is, mathematically, the hot, dense beginning of the next. The death of one cosmos is the Big Bang of another. He calls each of these universes an aeon, and the chain of aeons runs forever, each one's ending becoming the next one's beginning, without first and without last. And then there is the strangest family of all, the one with its roots in string theory. To explain it, we have to take a small step into one of the most ambitious and contested ideas in modern physics. In the year 1995, the American theoretical physicist Edward Witten made an announcement that electrified the world of string theory. For decades, the theory had fractured into several competing versions, each trying to describe all of nature as the vibrations of tiny one-dimensional strings, and the disagreement among them had divided the field. Witten argued that all of those competing versions could be true at once, if they were understood as different faces of a single framework existing in 11 dimensions, far more than the 4 dimensions of space and time we experience. In this framework, our entire universe, everything we can see and touch, all 3 dimensions of space, and the one of time, may be only a thin slice of a much larger reality, a kind of membrane or brain floating in a higher dimensional space that physicists call the bulk. And if our universe is a brain, then perhaps it is not alone. Perhaps there are other brains drifting in the bulk alongside it, and perhaps, long ago, 2 of them collided. The energy released by that collision of higher dimensional membranes in this picture is what provided the force for our Big Bang and the expansion that followed. Our universe was born not from a point and not from a bounce, but from an impact in a space we cannot see, a crash between worlds in dimensions our senses can never reach. This model is sometimes called the EK pyrotic model, a name drawn from an ancient Greek idea of a world born in fire, and like the bounce, it can be made cyclic. The brains, drawn back together by their mutual tension, would eventually collide again, ending our universe after perhaps 1 trillion years and beginning yet another in a collision we are utterly unable to picture, let alone comprehend. Notice what all 3 of these ideas have in common, because it is the quiet point underneath all the strangeness. Each one answers the question of what caused the Big Bang by pointing to something before it, a previous contraction, a previous aeon, a previous collision. Each one replaces the uncomfortable idea of an absolute beginning with the more familiar comfort of cause and effect, a universe caused by a prior universe. And each one, of course, only pushes the deepest question back a single step. If our Big Bang was caused by a previous universe, then what caused that one? If the eons run forever, what set the whole endless chain in motion? Or has it truly been running for eternity, with no first link at all? We have not escaped the question. We have only moved it further away into a previous cosmos we can never observe. It is worth asking why these cyclic and pre-Big Bang pictures are so appealing, because the appeal tells us something about ourselves. Each of them, in its own way, restores the comfort that an absolute beginning takes away. A universe caused by a previous universe is a universe that obeys the rule we live by, the the rule that everything has a cause that came before it. We do not have to confront the dizzying idea of a first moment with nothing prior, because there is always a prior, another aeon, another bounce, another collision stretching back. These models let us keep cause and effect intact all the way down by refusing to ever reach a true bottom. And there is something deeply human in that preference. We are creatures of story, and stories have earlier chapters. A cosmos that simply begins with no page before page 1 feels less like a story than like a story torn from its binding, and we instinctively reach for the missing pages even when there may be none to find. But preference is not evidence, and this is where the discipline of science has to reassert itself against the pull of what we would like to be true. A model can be beautiful, can satisfy our hunger for a cause, can be built by some of the finest minds alive, and still be wrong or simply untested. What would it take to know whether any of these pictures is real? Each of them, to earn its place, must point to some trace it would leave in the world we can actually measure, some subtle pattern in the relic radiation, some signature in the way the early universe was wrinkled, something that would distinguish a bounce from a collision from a single inflationary burst. Physicists are searching for exactly such signatures right now, in ever more precise maps of the oldest light, and so far, the sky has not clearly chosen between them. The models remain candidates, waiting on evidence that may or may not ever arrive, and that is the crucial honesty here. The big bounce, the conformal cycles, and the colliding brains are all genuine, serious work by brilliant people, sitting at the bleeding edge of modern cosmology. Like all good theories, they try to make predictions that we could, in principle, test through observation, but so far, not one of them has produced clear evidence in its favour. They remain, for now, highly informed speculation, possibilities rather than proven facts. Beautiful mathematical stories about a before that Hawking warned us may not even exist. Which brings us back, after this long journey through fleeing galaxies and accidental hisses and colliding worlds, to the question we started with. The simple question a child asks in the dark. What or who actually caused the Big Bang? And it is time, at last, to face it honestly. Part 11. What or who? We have come a long way from the chapel in Belgium. We have followed the expanding universe from a priest's reverse chronology, imagining, through the fleeing galaxies at Mount Wilson, through Einstein's discomfort and Hoyle's scorn, through the accidental discovery of the relic heat of the beginning, into the strange physics of inflation, the dissolving question of a before, and the endless chains of bouncing and colliding universes. And after all of it, we arrive at a destination that may feel, at first, like a disappointment, but which I want to convince you is something closer to a gift. We do not know what caused the Big Bang. We may never know. And that not knowing has a precise and beautiful shape. Remember the line drawn in the cosmic sand. Perhaps the Big Bang is not the beginning of the universe at all, but rather that line, marking the limit of our own understanding. Not a true starting point, but the place where our finest theories run out of road and the words we rely on stop meaning anything. Seen this way, the Big Bang is not a beginning so much as the opening of a history whose first chapters are hidden from us. It is perhaps not the first page of the story, but the first page that we can actually read. The earlier pages may exist, written in a physics we have not yet discovered, or they may not exist at all in any sense we could recognize. But the page where the writing becomes legible to us, the page where the universe first begins to make sense in the language of our equations, that is the Big Bang. It is the opening paragraph, several pages into a book whose beginning we cannot find, but the first paragraph that makes any real sense to minds like ours. Let yourself stand at that line one last time. Run the universe backward with me, the way Lemaitre did in his chapel. The galaxies rush together. The stars unform and scatter back into clouds of gas. The atoms break apart into a glowing fog, and the fog dissolves into a sea of pure energy, hotter and denser at every step. The equations carry you faithfully back and back until you reach that final sliver of a second where inflation roared, and then you push past even that toward the first instant. And there, at the very edge, the language itself begins to fail. The word before loses its meaning, because time may curve and cap off behind you like the surface of the earth at the pole. The word outside loses its meaning, because there may be no space beyond the cosmos for an outside to be. The word cause begins to wobble, because cause needs a before, and the before may simply not be there. You stand at the line in the sand, and it is not a wall you crash against. It is a horizon that recedes as you approach, a place where the map runs out, not necessarily because the territory ends, but because our charts do. And standing there, in that strange and quiet place, you are not meant to feel fear. You are meant to feel the particular peace of having walked as far as walking can take you. This is where Hawking's image returns and asks its hardest question of all. We wondered the whole way through what came before the Big Bang, what caused it, what or who set it going. But perhaps asking what caused the beginning is the same kind of mistake as asking what is south of the South Pole. Perhaps it is a sentence that obeys all the rules of grammar and points at nothing. We are creatures who cannot help but ask it, because our entire experience is built from causes and befores. But the universe is under no obligation to answer a question simply because we are compelled to pose it. The demand for a cause may be a feature of our minds, not a feature of the cosmos. And there is a strange freedom in that thought, if you let it settle. The universe may not need a trigger, not because it pulled its own trigger, but because there was no room, no moment, no outside in which a trigger could ever have been pulled. And now, gently, we come back to the priest. Return to Georges Lemay, kneeling in the wood-panelled chapel in 1927, the candle lit, the first stars showing through the tall windows. Here is a man who believed, with his whole life, in a creator. He had every reason, more than anyone in this entire story, to look at the beginning of the universe and see the fingerprint of God upon it, to write the who directly into his primeval atom. And he refused. He kept his physics and his faith in separate rooms, on principle, and when others tried to use his Big Bang as proof of Genesis, he gently asked them to stop. He understood something that the whole century after him would slowly confirm. Science, properly done, does not disprove a creator, and it does not prove one either. What it has done, over 100 patient years, is something more modest and more honest. It has shown that a beginning does not force a who, that the universe can be described, as far as our descriptions reach, as the lawful unfolding of natural processes, with no external hand required to start them. And at the very edge, where even those descriptions fail, it has fallen silent and admitted that it does not know. That silence is not empty. That is the thing I most want you to carry away with you tonight. When a scientist says we do not know what caused the Big Bang, it is not the silence of defeat. It is the silence of a mind that has walked all the way to the edge of the knowable and stopped, honestly, at the line in the sand, rather than filling the unknown with a comfortable story it cannot support. The what may yet have an answer we have not found, some deeper physics that will one day let us read the pages before the Big Bang. The who may be there, beyond the reach of any instrument, in a place where physics is simply not the right language to ask. Or the question may dissolve entirely, the way before dissolves at the first instant, the way south dissolves at the pole. We do not know which of these is true, and we can look at that not knowing, as Lemaitre looked at his starlight, not with frustration, but with wonder. Let yourself feel, for a moment, how unusual that posture is, because it runs against almost everything in our nature. When a human being meets a mystery this large, The oldest instinct of all is to fill it, quickly, with an answer that lets the discomfort stop. For most of history, the empty space at the beginning was filled with a creator, and that filling brought real comfort and real meaning to countless lives. In our own century, others have filled it instead with a confident materialism that claims more certainty than the physics can actually support, insisting the question is closed when it is not. Both are ways of refusing to stand at the line in the sand without an answer in hand. What Lemaitre modelled, and what the most honest physicists model still, is the harder and rarer thing. It is the willingness to hold the question open, to say the words we do not know and mean them, and to find in that uncertainty, not anxiety but a kind of spaciousness, the room that an unanswered question leaves for genuine wonder. And notice what the science has and has not done to the old division between the what and the who. It has not banished the who. No equation rules out a creator, and no telescope could ever photograph the absence of one. What the long century of work has done is quieter and more precise. It has steadily shown that a beginning does not, by itself, force a who, that the universe can be described, as far as our descriptions reach, as the lawful unfolding of natural processes that need no external hand to begin them. It has converted question after question that once required an agent, a who, into questions about mechanisms, about what, and at the very edge, it has begun to whisper that even the demand for a cause might be a question that dissolves, rather than a question that waits to be answered. That is a real shift, and an honest one. But it stops short, carefully, of the grand claim either side wants it to make. It neither installs a creator nor evicts one. It simply maps, with extraordinary precision, the boundary of what physics can say, and then it goes quiet, exactly where quiet is the only honest sound. Look up, the next time you are under a clear night sky, and consider what you are seeing. The light reaching your eyes has travelled across an expanding cosmos for millions or billions of years, stretched and reddened by the swelling of space itself, the same expansion that points all the way back to a hot, dense beginning some 13.8 billion years ago. You are made of atoms that were forged in stars that died before the sun was born, and those atoms trace their lineage, unbroken, all the way back to that first fraction of a second we cannot enter. The question of what, or who, caused the Big Bang is not an abstract puzzle for physicists in distant laboratories. It is the question of where you came from, of where everything came from, asked at the largest possible scale. Our ordinary minds, assembled from the very matter the universe produced, may never be built to comprehend the real answer, if there even is an answer to comprehend. But we can keep asking. We can keep building our telescopes and our theories and our beautiful speculative stories. We can keep walking toward the line in the sand, knowing we may never cross it. And we can keep trying, patiently and without fear, to see a little further through the fog.